Hi, welcome back to CFD Simplified. In today's tutorial, we'll simulate a classic hot room problem in OpenFOAM. This simple yet powerful case helps us understand the concept of natural convection and thermal buoyancy effect, perfect for understanding thermofluid simulations in OpenFOAM. So what are you waiting for? Let's get started. So this hot room tutorial is a very simple tutorial, but yeah, I thought that okay, let me explain the domain first. So basically what will be happening is like a room is there, we can say a rectangular room is there. Okay, this is we can say a rectangular room, and here at the bottom what has been done is like given a source. Okay, it is a heat source is being given. Okay, so like inside the this room, okay, it is like normal air is there. Okay, and this is a heat source. Okay, so some amount of some like not a heat source, we can say a hot source is there, because here we are not defining the heat, we are giving the temperature. Basically we will be giving the temperature as the input. All right, so that is the thing. So with that temperature, so this portion will get heated, and because of this, due to the natural convection, it will be heating the room, it will be changing the temperature of the room. All right, so basically this is the concept behind this simulation. All right, so let's see why I was, because it's a simple one. Okay, but why I choose to make the tutorial on this, you will find it while we will be making the simulations. Okay, so let's move on to the simulation part. Before we continue, if you are working on a CFD, OpenFOAM or engineering simulation project and need personalized help, I now offer paid support and consulting. Whether it's setting up your case, debugging issues, or developing custom solvers, I'm here to help you move forward faster and more confidently. Just reach out via email in the description. Let's make your project a success. Alright, so let's just start the tutorial. So if you can, it is present in the OpenFOAM tutorial. So first I'll show you where it is present. So first we have to open Foam tutorials, then we have to go to heat transfer. There we have to go to buoyant, Bosniak, simple foam, and yes, there you got hot room. All right, hot room. So this is the case. All right, so as in the Bernard cell tutorial, if you have not watched, please go and watch it. So there I have told you all that I've already copied the whole heat transfer tutorial to my home directory. So I'll be going to my home directory and simulating there this hot room tutorial. All right, so let's go back, press cd, press ls. Okay, so you can see that the heat transfer tutorial directory is there. So I have to go there, go to buoyant, Bosniak, pimple foam, and there you can find hot room. Okay, yes, so you can see the files written because I have already ran the simulation, because before making the tutorial I ran the simulation first to check whether it is running or not. So that's why I ran. Okay, so I'll clean the case with the help of all clean. So all clean. Okay, everything is gone. All right, so let me clear the screen, the terminal. Okay, yeah, so ls. All right, so first we will go to all run to check what are things are there. Okay, so it's very simple. First we have to restore 0, directory, then we have to run blockMesh, then we have to run set fields, then we have to run the solver. Okay, it's very simple. But yeah, if it is not there, how you can do that? So you can see here that 0 directory is not there. OpenFOAM will not read the 0.org. Okay, OpenFOAM will read 0 directory. So what you have to do first, you have to copy this 0.org to 0. Okay, you can see that 0 directory has been made, and inside that 0 directory all the boundary conditions are there. All right, next we will go to the system. If all run file is not given, then how to you have to run it. Okay, then you can see that blockMesh dict is there, set fields dict is there. Okay, so first you have to run blockMesh, then you have to run set fields, and then after that you have to run the solver. Okay, so let's run that. So first we will go back, we are in the hot room directory, then we will run blockMesh. Mesh has been made. I will again clear the terminal. Okay, you can see that mesh has been made with no error. Okay, I'll clear the terminal. All right, so then I will just run set fields. Okay, everything is set. Now I will again clear the terminal and run this, because this is the name of the solver. So I will just copy this, paste here, press enter. Okay, so yes, it is running fine. It will take around some seconds or 1 minute to complete. I don't remember the time, because I think the maximum time is 2500 seconds. So right now it has reached up to 1400, 1500, because mesh is very, it's not much fine, and that much is not required. Yes, 2000 step. Okay, fine. So it is written, press ls, you can find that the time step is written, and our simulation is complete. Okay, so alright, let's first check the results in ParaView. Then I will just show you, like, I will tell you about the why set fields is there basically. Okay, oh, what I have done, directly open ParaView. Okay, no issues. That ParaView can open. Will open this one from there. Open home.home. Okay, so yeah, so first we will go to check the domain. So this is the domain. I will just go to Wireframe to tell you about the mesh. This is the mesh generated. You can see that it's not much finer. It's basically a coarse mesh, and I think it's a perfect one. Nothing finer is being required for this. It's a perfect mesh. Okay, yes, it's good to have as much less number of nodes as you can, because you know, as an CFD engineer, you must be, knowing about how much computational costly it will be. Okay, so let's go to temperature. Okay, as I have told you that nothing is like here, they are not giving heat as an input. They have made one source here, and they are increasing the temperature of the source they have given as different. All right, so let's go to the surface and check. You can see that only the temperature of this part, like this portion where the hot source has been given, that is only raised, because the temperature of hot source has been given as 600 kelvins. Other temperatures are given as, other room temperatures are 300 kelvin. Okay, so if we measure, you can see that only the nearby surface of this hot one, like only that one temperature has raised. Otherwise here and everywhere the temperature is same. With the from this one, you can see from the color map, you can see that the contour is coming to be blue only, and that blue indicates that the temperature is 300 kelvin. No change in the temperature is being, you can see. Okay, why you cannot see? I'll just forward this to up to 2000. So yeah, I mean, you can see that nothing you can see, no change in temperature you can see. We can plot it with the help of This one also plot with over line. Yeah. So where is the line? Yes, here is the line. So if I just take it to the top, basically this line, and I'm just taking it to the top, and yeah, it's not perfect, but yeah, I'm just for the representation purpose, I'm just giving it. And here I will just press apply. Okay, so you can see that plotting has been done. So I will just remove other like the velocity, the alpha, epsilon, k, naught, p, p rho, gh, only to check the temperature. Only temperature is there, right? So here you can see that it's like 300 from the starting of the line. It is dropping at 300.28, then it is dropping, and yeah, it is like this. So basically it has increased, but very less amount of increase, like 0.28 Kelvin. You can see that that is the temperature difference. Okay, then so yeah, you can see that the maximum temperature is coming out to be 300.28, because the ambient temperature initially it is given as 300 Kelvin. So it is there, temperature change is there, but it is very less. Okay, because why? I will tell you the reason why. Because I will tell you the reason, right? I will tell you the reason. So if you can go to the velocity, let me show you the velocity, because velocity is required to know. Okay, here you, yes. So you can see that everywhere the velocity is coming out to be 0 only. You can see, or we can just let us check from here. Plot over line, and what we will do. Let's again make the this one, the line again. Okay, so this is the line, this is the line, press apply. Okay, temperature हटाओ, alpha t, epsilon, k, naught, p, pr, rho, gh, and nut also, which is new t basically. So regarding the velocity, you can see that into the upper portion it is like from 0 it is raising up to 0.02, then it is decreasing, then it is reaching up to the maximum of 0.1 meter per second, then it is again coming out to be 0, which is that portion. Okay, so here you cannot see. So because that is a very small amount of the velocity, to because the the air has to flow. Okay, because the transfer medium will be air only, due to which hot air only, due to which the that hot air will become a medium, and due to which that temperature change will take place. All right, so here the hot source is there, and from there the air will the hot air will come, and it will reach the other parts of the room. All right, so because the temperature is very low, so we can say that, okay, or we have to run it to many larger time step. All right, then we can say we can see a significant change in the temperature. All right, that is the part. So yes, this is the thing, but temperature change you have seen, and velocity is also there. Okay, all right. So do you want to get to make it like to change the temperature fast? You must have seen the example of a blower. In the winters, like we use heat blowers. What it does, it is having a heat source inside it. you know with the help of the electricity that got that there's a coil, it got heated, and due to that heated coil a blower is there. If you just we only control the fan speed, all right, we do not control the temperature. The heat and the temperature remains the same. We only control the the fan speed. With the help of the fan speed we can just control the like how we want more heat or we want lesser heat. All right, so if the fan is not there, and if you just switch on the the coil, okay, the coil is switched on, the blower is switched on, but fan you have switched off. I'm having that a blower there. In that one, this function is there. It's like you can just switch off the fan, and the coil will be on. Now what will happen with that? So what will happen is like it will, you know, it will just like it doesn't supply heat to the to my room. All right, like I'm just sitting here. I'm sitting here and I'm just keeping the heat, the blower here. It will not cover this much distance also. Like this is the blower, and I'm this is the blower and I'm sitting here, so it will not be able to cover this small distance also, because flow of air, the velocity of air is very low, which is inside the room only. We have to give some type of external thing, like external force convection thing, that we have to give. All right, so or another part we can do is like we can increase the air speed in the room. That I cannot do. Okay, so only thing is that we can increase the speed of the air coming out from the blower. All right, so that is the part. Yeah, we can control the heat, like heat we can control, but yeah, fan speed also we can also control. And with the help of, I think I missed that part while I was explaining about the blower. But yeah, this is the thing. All right, this is the thing. So we can also see a significant temperature change. How? Let's close this one. All right, and let's go. Now I will just tell you about this set fields. Okay, set fields. Yes, so with the help of the set fields, they have make the make this source, this temperature source, given the temperature to the to that source. Okay, you can see that 600 Kelvin is there. So this is the temperature they have given to the source. This is the the coordinates of that one, of that small source, okay, which has to be there. And this is the volume scalar field, which is basically the temperature of the volume, the other parts, the temperature of the, what will be the temperature inside the room. Basically with the help of this you are defining. Okay, they have not defined with the help of the boundary condition. Basically we just define all those things with the help of the boundary condition, that if we'll go inside 0 and if we'll go inside t, so you will find that floor they have given, and one 400, another 300, 300, 300, 300 is there. Okay, ceiling they have given fixed value, uniform 300, fixed wall 0 gradient, and others I don't know why, which this type of like non-uniform list scalar they have given to make it like 300. So basically they are just floor, other parts of the floor, basically they are giving the 300 value. Okay, that is the thing. So yeah, but here they are not telling that what will be the temperature of that source. Okay, nano u, it will go to the velocity, floor no slip, ceiling no slip, fixed walls no slip. Okay, uh, others I think they are just k epsilon r for the turbulence, and mu t p p rho jh. We don't have to worry about that. We are only focusing on temperature and velocity, because these are the two factors which are responsible for the simulation, basically for the results which we are focusing on. All right, so yeah, let's increase the thing. So first we will go to the system and we will go to set field state, So yeah, here I'm not changing the value of the temperature. Let's keep it to 600 Kelvin. All right. What I will do, I will go to the boundary condition. I will go to okay. All right. First, let me clean the case. Okay. Should I clean the case or should I make a comparison? Yes, let us make a comparison. Okay, that will be a very good representation of the result. I think I have made no. All right, so let me make a directory hot room 2. Right, it is there. So let's go inside hot room 2 and uh, copy the path. Clear. Go back. Go to the transfer. Sonic simple form. Go inside hot room. All right. So what I will do, I will just copy some files. All right. I'll just copy cp-r 0.org constant system to the directory, to my directory. All right, let us open one more tab, and here I will go to hot room 2, and yes, all the things are there. Okay, so first let us copy the 0.org to 0 directory. What I am doing, man. ls, yes, it is there. Then we will run the blockMesh. Okay, yes, it is there. Or let us clear the terminal. First change the value of the velocity, because now here the to increase the temperature of the room, basically significant increase in the temperature of the room, the velocity will play the role. All right, we have to increase the velocity. So what we will do, we will go inside the velocity boundary condition, and here you can see that internal field is there. So basically it is telling us that okay, this is the velocity we are giving, uniform 0 0 0, and all the x, ux, uy, uz all are 0 initially they are given. So what we will do, we will initially what we will give some value. Okay, so I'll be giving 2 uh, just like 2 meter per second in y and 2 meter per second in z. All right, yes. Then we will go back. Block mesh will not affect, but yeah, we will run it once again. Clear the terminal, set fields. Okay, fields are set. Now we will run the this one, the solver. Okay, yes, press enter. No, from morning till evening I'm just sitting here only. I got bored. When I get bored, I just drink something, because I'm on diet. uh, so I'm not eating much because I'm a very heavy snacks eater. I was, now I've left. I'm just drinking some things. I got bored, so to do the work also. Yeah, yeah. So let's come back. Okay, these are there. So let's write down the foam, right? Then we will go to paraview.exe foam.foam. Apply temperature. Yes, you can see that on the above the color is different. Here the color is different. All right, you can see that temperature change has happened. All right. Yes. So the purpose of this, like, okay, I might not have taken only the correct velocity or something like that. Only the purpose was like, if you wanted to change the temperature, if you like, you really wanted to know, like, what you can do in this case, like, like if you wanted to see like how much heat is being dissipated from like like from something like if you wanted to check the case of the blower only, like I wanted to check. So with the help of this hot room tutorial, you can check that one. Okay, you can check that one. All right, you can place this one to, like, right now the source is on the floor, pointing towards the ceiling. Generally it will be on either on this side of the wall, on this side of the wall, on the basically on the sides basically. That is the thing, it will not be on the floor. So you can just make this one on this side, on this side, on this side, on this side, and you run the blower. Okay, give a temperature, give a temperature of 20 degrees Celsius, and then you run that one. Give some velocity, it will throw. Give some temperature, it will having. Okay, and then you can see that how the flow is happening and how it is uh, supplying the hot air to the room and increasing the temperature of the room. All right. So let's check it with the help of the line. Line. Here it is. Okay, I'll just put it here. If you wanted to compare, then you have to, make the line on the same coordinates. In both the case, you have to make the line on same coordinates. I'm just taking it randomly. Don't worry about that. But yeah, you have to, if you are making some credible results, then yeah, you have to do it like that. U magnitude alpha t epsilon k mu chi p p r g h. Only temperature is there. You can see that. What value you are giving, man? Array? Initial temperature is 190 Kelvin. Okay. Because when I ran this one, I got, it was not 190. It's something else. I'm sorry. Sorry. All right. I'll be back. Let me check and then I'll be back. All right. So basically, what has happened is like, no. So because we have increased the air velocity, the temperature has, initially it has decreased at the 400 seconds. It has reached up to, you know 250 degrees Celsius. So it is coming like this. So in the color map, no, I want in the color map, no, yes, here it is now. Let's make it 300 only. Apply. Okay, now you please tell us how much it is there. It's temperature only, and success spirit filter sample reticle plot line here for supply. It is coming like this. Serial K, UTP, PVGH. Yes, because we have increased the velocity, this was happening. But yeah, you can see that significant increase in the temperature. You can see it is happening. Like before, it was, not much increase in the temperature we can see. But yeah, with the help of the velocity, there is significant increase in the temperature we can see. Like, okay, it is there. All right. So, like basically, what I wanted to tell you is like you can, simulate, a result like this with the help of this one buoyant pimple phone. Or if you wanted to simulate to check for the cooling also, I think it will work. Okay, like if you wanted to, there is a room and you wanted to check like how much, you know like if you are supplying this much of flow rate, how much cooling is happening. Okay, so like thermal, like cooling analysis you are doing, so you can do it. Define a patch, give some temperature, give some velocity, and then you check like how much cooling is happening. So I think this is a good way of checking it. All right. So yeah, I mean, the illustration was for the natural convection. I made it to a forced convection, but just wanted to give you a brief idea of these things. Okay. So yeah, I mean, yeah, right. So if you want to check about the this one, we'll go to, let's close this. Let's close this one. Yeah. So if you check the velocity has decreased up to 0.045, 0.45 it is gone. Okay. Alright, so something has happened, something must have happened, because when I ran, no, I'm just telling you, like when I ran, there was a proper, simulation and all those things were there. Okay, so my point was like to give you, like to show you like how you can change the values, like okay, the velocity values, the temperature if you want to change. Okay, so that is the part. All right, so yeah, I mean, this was the tutorial. And so like in this hot room simulation, this is a great way to understand natural convection and thermal buoyancy in OpenFOAM. It's simple, fast, and provides deep insights into indoor thermal comfort, room ventilation, and passive cooling techniques. Okay, so thank you for watching. We'll meet you in the next tutorial. Take care till then. If you found this helpful, please like, share, and subscribe to CFD Simplified. And don't forget to check the description for download links and additional resources. Thanks for watching and see you in the next tutorial.